I said, I'm Ricardo. I work for CERN in Geneva. And today I'll be talking to you about what I call an almost perfect match in the cloud native and scientific computing. And I'll talk more on the path of what has been the journey of containers and cloud native for this kind of workload, and a bit about the technical part as well. So yeah, hope I'll leave some time for questions. So very quickly, I'm a computing engineer at CERN. I work mostly on Kubernetes and containerization. I do quite a bit of GPUs and machine learning infrastructure as well. I have a couple of roles in the Cloud Native Computing Foundation. So I helped CERN join the foundation as an end user. In the meantime, I joined also the Technical Oversight Committee, representing end users there. And this is kind of the body that oversees the projects and follows them in their maturity graduation. I also co-lead the CNCF Research User Group with someone from Research, Jamie Poole. And I've been co-chairing the last two KubeCons, and I actually will do the last one in October, and then I pass the one. So very quickly, why am I giving this talk is because since the start, containers had gained quite a lot of traction in the scientific community and research communities. And there are a couple of reasons for that. The first one is not specific to scientific computing, which is workload isolation. The ability to do the same that you can do with virtual machines, but in a kind of a more lightweight way. That's one. Second one is reproducibility, and I would extend this to traceability as well. But for science, reproducibility is key. When you have your research, it's very important that you can share it and that people can redo it and validate your results. So containers help with that. And then simplification. This is, again, not specific to scientific computing, but because we have large resource requirements, any kind of simplification means that also we improve efficiency, so both for the infrastructure and the deployments. And then scalability and bursting, again, large scale means that we want to explore this as much as possible. So I'll cover some of these topics, but I will start with a couple of questions. So one thing that scientists and researchers often have to deal with is, okay, I have my data, I'm doing my research now, can I actually do the same with this data in 10 years? Can someone come in 10 years and try to reproduce my results? And there's been a couple of initiatives around what's called open data, and I give the example of the CERN open data portal, but this is really not specific to CERN. There's many other organizations that are focusing on making sure that the data is not locked in and that everyone can get access to it. So CERN publishes a lot of the data that comes from the Large Hadron Collider, from the different experiments, but what we very quickly realized is that data is not enough. So there was a couple of colleagues of mine that published an article in Nature magazine where they made the case that open data is a start, but it's not the whole thing. You also need to be able to share your software and make sure that it can run. So the highlight for this topic of this article was that the researchers can be confident that their code will remain usable whichever platform they choose. And this is the claim that containers allow to do this. And if you think about it, the way you define a container, all the stuff that goes in a Docker file or whatever you're using to generate your container, it kind of defines what the computing environment should be for your analysis. So this is the statement that they were doing, and they were saying focusing on data is also not enough. It needs to be accompanied by software. So this is the main point. And this is where this was the moment, like people were already using containers for kind of making their life easier, to kind of quickly come up with a nice computing environment and share it with their colleagues. But then we started realizing that this could be done for other purposes as well. Second question is like, now you have your software, you containerized it, you can share it, you can reproduce it, but can you actually run this container in 10 years? So this was always a problem. If you look back in time, evolving infrastructure is always a problem. And I put here a nice screenshot from an article from from the CERN records, where it tells you about the evolution of Unix and all the variations of Unix. If you go through the CERN archives, you will see a lot of history about the computing evolution. And the usage of Unix was quite large, anything from HP Unix, AIX, Solaris, you name it. And the main thing is that depending on the platform you want to use, you had to change the way you compile your software, you had to tune it differently, which means that you probably don't have a reusable component. Like if the infrastructure evolves, you probably will kind of lose the ability to run your code, which is bad and breaks the idea of reproducibility. It also means that you have to evolve the infrastructure and your applications together. So if there is no isolation concept, then it means that your code is running directly on the platforms, which means that when these platforms need an upgrade, your application has to evolve with it, which makes it really complicated when you're working on collaborations of hundreds or thousands of people. And this is Unix, and then came the Linux era, so that was until 2002. And then if you look at the Linux evolution, again at CERN, you see that we started what we call SLC, which is Scientific Linux CERN, which is just a Linux distribution based on Red Hat platforms. And you can see the evolution of like GCC, and I'm just giving GCC as an example. All the libraries will have similar problems. And you can see that there's a big jump. So, for example, migrating from SLC4 to SLC5 was a massive endeavor because we had to migrate all the applications to support the new versions of GCC, be updated, all these things. Whatever wasn't updated, basically, is kind of lost. So this idea of separating the infrastructure from the applications is something that also containers give us in a really nice way. So again, I highlight here, evolving infrastructure and applications separately. The idea of having a shared kernel, but it's kind of enabling you to run different operating systems in the same kernel, which is really nice. Does this separation nicely. And then the fact that these are immutable makes it them also helps for reproducibility. Of course, you need like a very, this is a slide that I showed when we first started looking at containerization at CERN, but of course you have to version things properly inside, make sure everything is pinned. But this capability is there. And then you can start thinking, the developers have their builds, their codes, they share them in a public registry, and then whoever are the users or the customers of your code will pull it from there in a nice way with a clear separation of roles. Here's an example. With a colleague, Lukas, we did a demo a couple of years ago. And the idea was really to take a very old component, well, not very old, but like more than decade-old component code that was generated when we first were doing the first analysis for the Higgs boson, when we got the first amount of data from the Large Hadron Collider. And then, like 10 years later or something, we took that code with a completely different infrastructure, running even not on CERN resources, and we could just pop it in, and it just works. And this kind of like is shocking for people that have been dealing with these problems for a long time. So the move to cloud native for these other reasons kind of gave us this idea of analysis preservation as a byproduct of this process. This is quite a big difference also to running virtualization in the sense that it's much easier. The platform is really developed to enable this kind of thing. Now, talked about infrastructure evolving these components. I mentioned in the beginning another motivation was scalability. So can this help me to also scale my workloads? You now have something that you tried on your computer, containerized, shared with your friends or your colleagues. Now I want to see if I can run it faster. Can all of this help me? So I will tell you, this is an actual example. It's really a cloud-native showcase of what is possible with this. We had a user that came to my office and she asked me, I have this script. I've been running this to train my models, my machine learning models. I've heard that containers might help me go from one GPU to more. And I'm kind of stuck. I have a virtual machine with a GPU. I don't know what to do. So we sat for a bit, And we started by the first process, which is what we just discussed, which is take her script, her requirements, containerize it, make it nice, and then suddenly we can run in a Docker container, which means that she doesn't need her custom VM anymore. She just needs Docker installed, and she can access a lot more resources in a much easier way. So we could go to the public clouds and run a Docker container on a single node if there would be GPUs there. But she didn't want just to stop there. She wanted to do distributed training. So then this is where orchestration comes to the game. So we had the first step of containerization. Then we start looking at orchestration, which is to take one single component, distribute it across tens, hundreds, thousands of nodes, and make them work together. And this means that you need a way to actually define and express your requirements in a declarative way, and then you delegate to the system that will take care of spreading the deployment and make things talk to each other. So we started by trying this using pure Kubernetes, which meant we still had to handle the communication between the jobs. So it's not just her code. We had to set up like a SSH key so that they can talk to each other. The original component was based on MPI. But then we started looking at abstractions that build on top of Kubernetes that allow us to do kind of scientific computing. And one component that we started relying on is Kubeflow, which is kind of a machine learning platform on top of Kubernetes that allows you to define a TensorFlow job or a PyTorch job or an MXNet job. And that's all you need. And then the system itself will know how to make things talk to each other. So this is something we tried. She had it with one GPU. If she would train a single epoch, if you do a bit of machine learning, she wants to do several epochs. But if we need to do one epoch with one GPU, it was like 3,000 something seconds. Then suddenly we could do two GPUs, and we could go down to like half, and because the workload is actually very well behaved and scales linearly. But then we can go, as I mentioned, like you have containerized, you have infrastructure, you can use public clouds. There are managed Kubernetes services there, and you can scale to whatever you have access to. So we tried it up to 128 GPUs, and it kind of linearly scales as well. And this is for a physicist that doesn't necessarily understand or is interested in infrastructure. This is kind of shocking because suddenly like all these tools give her the abstraction that she wanted. This also means that with this kind of thing, the other part that is really nice is that if you are running if you have access to an HPC, a supercomputing center, then you probably are okay. But if you're not, then you want to use the public cloud. So kind of paying on demand is something you want to do to reduce the cost. So this is an example of what the cost would be. Basically, because it linearly scales, we can do the same much faster and kind of a flat cost, apart from the last bit where it goes a bit up. So in summary, we started from a custom script from a user. Her training, one epoch, and she wanted to do like 100 epochs, takes 3,500 seconds, and then we achieved 100 times speed up. And this is really building on components that we are used to and know well, which meant it didn't take very long, actually. So this is a success story. Now, I come back to what I was just saying before, which is if you are a physicist in a large lab, you probably have access to a lot of resources. But if you leave the collaboration, you probably lose access to those resources. So do you actually how do you reproduce your analysis if these infrastructures disappear? If, for example, if you're running a big HPC farm, if the tender is not renewed and the resources disappear, what happens? So this, again, is where cloud native is kind of democratizing science, because all these components are used and important much beyond scientific computing. They are used by the industry heavily, which means that basically all the public cloud providers are offering managed Kubernetes services, supporting containers in a really nice way. So we wanted to do an experiment where we basically took the Higgs analysis from back in 2012, and we tried to redo it using modern infrastructure, and we got some help from the Google Cloud to try this. So basically, we had a data set of 70 terabytes that had 25,000 files. The software is single core, so we could go to 25,000 parallel jobs. Of course, depending on the amount of resources you have, this takes longer. Back in the days, this would take more than a day just for this small data set. If you think that we wanted to do this demo in kind of 15 minutes, we had to introduce it, so we had to run it in five minutes. So we kind of scaled the infrastructure by relying on this stack, and we had a cluster with 25,000 cores. We submitted the jobs, and then each job is actually only taking like 3 minutes. So we basically got it done in 5 minutes. But it really shows that if you have your code now and you're running an HPC farm, but you comply to this idea of containers as building blocks and cloud-native tooling like Kubernetes APIs as your interface, you open the possibility to run these things elsewhere. And in reality, because we only pay for what we use, you basically can find the Higgs with this data set for something like $250, which makes it really democratizing science. I think it's the good word here. So in the demo, we would see the run going, and we would build the Higgs plot, which always makes a physicist very excited, where you see the peak, the red peak building as we discover Higgs events in the data set. Now, how much is this actually used? I'm talking mostly about CERN examples. In this CNCF research user group, we kind of get together a bunch of different institutions, and you can see a lot of scientific institutions and research institutions, but you also see industry like G-Research and Red Hat are participating. Scalability, there's quite a lot of diversity there in the different areas that people come from. And also, we started asking which research areas do you support, and you see a kind of a pretty good variety there as well. And then, which kind of workloads do you support? And this is where it gets really interesting, because we're talking about things that are batch, maybe interactive workloads, machine learning, but then you see that they are using the same infrastructure for campus services. They are using the same thing for their storage systems and to support databases. And this is where things really start becoming also interesting, is that you're breaking this barrier between the infrastructure running your traditional IT services and the infrastructure running your scientific workloads. So there's a lot of room for consolidation here. And this is basically what I put here. In batch, you need a lot of resources. In interactive, you have very spiky behavior. In services, you have probably a steady deployment. But what we start seeing is that the same clusters where you're probably doing some machine learning or maybe some large-scale data analysis, you're also running maybe your financial services or the way people ask for paid leave or whatever engineering applications your users need, which is quite interesting. Another thing is what's the state of the usage, and this is also quite showing is that 75% of the people actually show they are using this in production today. There are some limitations, and I'll talk about them, but people are already using. I know this because we also do, but still. So things that people are doing, multi-cluster support. In this group, we discussed a lot about multi-cluster, notebooks, batch on Kubernetes, cloud bursting, image and software distribution, GPU sharing, and then integration with storage systems and authentication. So this is the dream picture, where you have a single cluster that is serving all your workloads, or maybe a single cluster view serving all your workloads. And there you are running like interactive notebooks. You're running Dask for scalable analysis. You're running Kubeflow for machine learning. And as we said, you're probably also running your traditional IT services. And your cluster supports multiple node pools, so you can onboard your new GPUs that just arrive, or you can scale to the cloud and go and do machine learning on Google TPUs or in Azure with IPUs. And then everything is properly isolated. You have quotas for each namespace. So this is the dream, and it's slowly building. Now, are we there yet? There's a couple of things that are there. Yeah, largely yes, I would say, but a couple of things that are clearly there and have been the evolution of the last couple of years. The first one is this idea of efficient software distribution. This is not the first thing you think about when you start playing with these tools, but when you start realizing that some of these images can be gigabytes or tens of gigabytes, you start getting scared if you talk about distributing jobs with thousands of replicas across thousands of nodes, all pulling gigabytes from your central registry. This is a really nice way to kill your system, and we have done it several times, and we learn from it. So one thing that we started pushing a lot is this idea of lazy pulling. Instead of the initial concept of having your layered images and pulling all the layers, which makes it really nice for reusability of the layers. But if you have to pull the full thing and your images are still gigabytes, it doesn't really scale very well. So we had a similar system at CERN for our workloads to distribute software before even containerization, which is called CERN VMFS, which is this idea that you push all your software in a central place, and then you have this kind of squid proxies across your different sites and servers that pull just the data that is actually needed on request. This is quite interesting. We run a workshop at CERN with a couple of people from different cloud native projects. Back in 2019, we had a nice discussion. There were some ideas already going on ContainerD, on this idea of remote snapshot, which is exactly what we are talking about. And in the end, this is already existing. So if you are deploying Kubernetes and containers today, you will see that there's this concept of stargz, which is a seekable targz, and this is exploring the idea that I just saw a tweet before coming here where someone says container images are just tarballs and JSON. Yes, so container images are just tarballs. And what someone that is really smart came up with is that a tarball of multiple tarballs, it's still a tarball. So they started playing with making tars of individual files, which makes it in the tar seekable. So you can actually access the files within the image very nicely. And this allows us to stop having this idea of downloading full layers, but only accessing the files when they are requested, which is exactly what we need. And I won't go a lot into details. I will just show you why this is important. If you have an image of multi-gigabytes, what we see is that the actual jobs pull around 6% of the image. So you're basically putting a huge load on your services and your infrastructure for not much. This kind of system improves this a lot. You can see the pulling time. Obviously, it's almost instantaneous. It's actually much faster than this now. But you can also see that the ingress, the amount of data that you're actually downloading is a lot lower as well. And this is an example with an 18 gigabyte image. And then you can see the exact execution time goes slightly up because you're actually pulling what you need during the execution. But still, overall, this is a huge gain. And then the second part is scalability. I would say that we are also there on scalability. This was not the case a couple of years ago, but we are now able to schedule hundreds of thousands of concurrent jobs, and this is our requirement. I put here again a CERN example. We have this very large distributed infrastructure across the world with 200 sites that serve the Large Hadron Collider computational needs. And you can see here an example from one of our experiments. You probably cannot read, but at any moment you will have between 300 and 400,000 jobs running just from one experiment, and we have 4 of this size. So we need the scale. And we took this as an example of can we use Kubernetes to replace the grid, which is pretty bold. And the first experiment showed mixed results. We started learning a lot about killing ourselves and the cluster, and then we started learning also about tuning the scheduler to make things better, to optimize the usage of resources. You can see these holes that show that not everything is great, and we want to optimize that, of course. But this was a test cluster with 2,000 cores in 2018. Fast forward to today, my colleagues just gave a presentation a couple of months ago where the same experiment, Atlas, is showing how they are running a 100,000 core single cluster in the public cloud, in this case in the Google Cloud. And you can see the last plot there, they can run this steadily for multiple days, and with a similar efficiency to other resources we have. So this is really shows how the community has put the effort that was needed and kind of rise to the needs. But there are a couple of missing bits, and this is the last bit I will talk about. So one thing that we need is advanced scheduling concepts in scientific computing. It's not just submitting your pod or your jobs and having them pending and then the cluster auto-scales or something. We actually need to submit a lot and have a way to queue and prioritize the workloads. This is not something that exists in core Kubernetes. And then when you have this kind of multiple collaborations or experiments or groups running workloads in the same cluster, you want to do something that's called fair sharing, which is more than quotas. You want to, even when one of the groups is kind of not filling up their quota, you want to make the best use of the overall resources, so you allow others to kind of rise for a bit, and then over time you make it fair to everyone. And then concepts that are very keen for sort of MPI workloads, which is the idea of co-scheduling and index jobs, so that you can submit resources and they guarantee that they are submitted at the same time, because if you have 100 jobs that are codependent and one cannot be scheduled, then you're kind of taking the slots for not much or nothing. So there are different projects that are focused on this. One of them is Volcano. It's quite popular in the machine learning community as well. And it adds these notions to Kubernetes as custom resources. And this shows also that Kubernetes is really a platform. It started by supporting containerization, but actually you can do a lot more with it. And this notion of extending the concepts is quite nice. The other one that I mentioned is more recent. It's called Armada. And this focuses on the same ideas of queuing, but it takes a multi-cluster approach. So it wants to kind of abstract the queuing from a single cluster or the scheduling from a single cluster and apply it to a multi-cluster environment. This is really nice if you also need to scale beyond, say, 5,000, 10,000 nodes, or if you want to onboard on-premises external resources into your on-premises infrastructure. And there's a working group that has been created in Kubernetes that is working on kind of getting all these concepts and making sure that they are well supported in core Kubernetes and in the scheduler. So they are focusing on evolving the job API so that you don't need new concepts in addition, and making sure that things like queuing, proper scheduling, auto-scaling are well supported, and then the optimization of the nodes as well. The goal of this is really for consolidation again, so that you will still need these additional projects probably, but you can rely on core components and concepts underneath. The other one is, I won't spend a lot of time on this, but it's large scale. None of this really is solving a lot of computing problems. None of this is really tackling the data problem. When you're talking about terabytes of petabytes of data, moving them around, these things have huge gravity. To move them around is really hard, especially if you're using public clouds. It's very easy to push data, but actually to get it is extremely expensive. So some sort of data-aware scheduling that will take that into account is quite important. And then networking, again, I just mentioned multi-cluster. There's a lot of networking concepts in the area of services with service mesh and the gateway API. None of this is really suitable for the workloads we're talking about, where the actual workloads need to talk to each other and they might be living in different data centers or definitely in different nodes. So these primitives for multi-cluster are really important. So in summary, I started by saying that containers helped with isolation, but what we saw is that they also help a lot with reproducibility, which is key in scientific computing. Then Kubernetes came up as an orchestrated, but it became more like a platform for scientific computing. All sorts of workloads are now running on top, and we start having these abstractions that allow us to more easily expose our needs to the system. And it's also breaking these barriers between your traditional IT and the scientific computing infrastructure. And this is something that is really changing the way we organize ourselves also in the IT departments. And then there are a lot of well-established components, but as we saw, the needs are still there for more. So it's an evolving ecosystem. So there's a lot of place for evolution, and a lot of place to do still really cool stuff. And that's it.
Thank you. Thank you so much, Ricardo. And we've got 3 questions, actually, and we have a little bit of time, so that's great. You're pretty much spot on. I think you're 1 minute over, so it's awesome.
Is it?
Perfect. So yeah, let's have a look at the first one. So the first question is, are there any drawbacks to using TPU SKUs in the public cloud? They seemed to be very cost-effective.
Yes, so I will go back to the slides. So they are extremely cost-effective. Where do I have it?
Can we see the slides at the same time as the questions? Is that possible?
Right.
Thanks.
So they are. That's the main motivation for TPUs from our experience. Is really they are extremely cost-effective. The drawbacks is that not all workloads can use tensor cores or TPUs. So if you're doing machine learning with TensorFlow, training neural networks or something, TPUs are great. They are really great. You need a way to manage them, meaning that you cannot get them on premises. You can only access them in the Google Cloud, which means that if you're training over a huge amount of data, you will have to upload it there. If you're renewing your data sets often, you have to track them and sync them. All of this is doable if you have the tools to actually handle that. It's a very good option, definitely. Yep.
Okay.
I don't know.
Back to the, yep, there we go. Yeah. You're on it. Any drawback, oh, sorry, I just read that one. What was the root cause for your master node running out of memory in 2018?
I think we've tried everything, so we still see them dying today. This was, the first, the main root cause is you can see that it's out of memory, which means it's just too small, so scaling it up kind of helps. But we also saw there were issues with when you start scheduling a lot of things. We saw at the beginning, Kubernetes had this limitation on the number of API requests you can do per second from the different components. When we started playing on bumping this to be able to schedule more workloads, we were a bit too aggressive to comply with our needs, and basically we started hammering the whole thing, and started dying also due to that. Then we added Prometheus monitoring, and we were running some components in the master, started dying due to this, so it was kind of like a learning experience.
All right, and I think there was one more question. Oh, wait, we've got 2 more coming in. How is this advanced scheduling supported or done by tools? Is it supported by Slurp or similar?
So that's a very good question. So this is right now, this is not compatible. Like if you're running Slurm, which would be like one of the standard tools for your HPC farm, there are a lot of people, or HTConder, there are a lot of people that are managing these tools with Kubernetes to simplify the deployment and the management of Slurm or HTConder, but they still rely on them for the scheduling. And this is the standard. Like there is no replacement right now. No one is completely replacing these systems. The idea is really to introduce the primitives that Slurm and HTConder offer for these advanced scheduling concepts into kind of core Kubernetes, and then we'll see how things evolve. The idea is that you will be able to do these workloads directly on Kubernetes, or maybe integrate them in a different way with the Slurm or HTConder, instead of having to have these 2 systems again.
Okay, and I think there was one more question. Am I assuming correctly that you don't use Kubernetes for data storage? If so, is it because of performance issues due to storage hierarchy?
It's really not. It depends what you mean by you don't use. Like we do use it. We integrate Kubernetes with our storage systems in terms of like if you want dynamic provisioning of your volumes, we integrate with our Ceph clusters or other systems we have in-house. So in this respect, we do integrate, but we have our storage systems for physics data that hold like exabytes of data. And in this case, you're not like managing this necessarily today with Kubernetes. We have these systems for a long time. People are looking into easing the management of the system, but my point here is really that when you're scheduling, you need to know where this data is. If this means integrating data completely into your clusters is maybe a possibility, but really here is the idea that data should be, the scheduler should be aware of the data. It doesn't matter if it's managed by the Kubernetes or not, but it should be possible to make these decisions. Ideally, it should be in the same place, but it doesn't really have to.
Okay, well, thank you so much. Another round of applause, please, for Ricardo.
Thank you.